Today I want to talk about quantum computing. Not the hype version, not the sci-fi version, but what it actually is, why it exists, and why it matters. Quantum computing didn't appear because classical computers are bad or outdated. It exists because classical computers, as powerful as they are, run into fundamental limits when problems become too complex. Classical computers process information using bits, zeros, and ones. They're incredible at everyday tasks, running software, browsing the web, training AI models, managing data and networks. But some problems scale in a way that makes classical computation explode in complexity. Not slow, impossible. That's where quantum computing comes in. Quantum computers use qubits, which behave according to the rules of quantum mechanics rather than classical physics. Unlike bits, qubits can exist in superposition, a combination of 0 and 1 at the same time, similar to a spinning coin that hasn't landed yet. Now, here's an important clarification. Quantum computers are not doing everything at once. That's a common misunderstanding. The real power comes from how quantum states interfere with each other while they're in superposition. Quantum algorithms carefully shape these states so wrong answers cancel out and correct answers reinforce each other. When you measure the system, the qubits collapse into a single result. That's quantum computing in one sentence, carefully shaping probabilities before measurement. Another key idea is entanglement. When qubits are entangled, their states become linked. Changing one instantly affects the other, no matter how far apart they are. Entanglement allows quantum computers to scale in power because the system behaves as a single connected whole rather than independent bits. But this power comes with a cost. Quantum states are extremely fragile. Heat, vibration, electromagnetic noise, even the environment itself can disturb a qubit and cause it to lose its quantum behavior. This process is called decoherence. Once decoherence happens, the computation fails. This is why quantum computers require extreme engineering. Superconducting qubits must be cooled to temperatures colder than outer space. Ion traps suspend individual atoms in electromagnetic fields inside ultra-high vacuums. Photonic systems require near-perfect optical pathways. Even then, errors happen constantly. That's why quantum error correction is one of the biggest challenges in the field. To create one reliable logical qubit, you may need hundreds or even thousands of physical qubits. So, what are quantum computers actually good for? They're not replacing your laptop. They're not running apps or browsing the internet. Quantum computers excel at very specific problem types, simulating molecules and materials, optimization problems with massive search spaces, certain cryptographic and number theoretic tasks, complex physical systems that classical computers can't model efficiently. This is why the future of computing isn't quantum instead of classical. It's quantum alongside classical. Classical computers handle control, interfaces, data, and AI. Quantum computers are used as specialized accelerators, called only when the problem demands them. Quantum computing isn't about speed for its own sake. It's about expanding what computation is even capable of. We're learning how to control nature at its most fundamental level, not to replace existing technology, but to solve problems that were previously out of reach. That's why quantum computing matters. And as the hardware improves, the algorithms mature, and error correction scales, we're just beginning to see what's possible. If this helped clarify what quantum computing really is, go ahead and like the video. And if you want more clear, no hype explanations of quantum mechanics, quantum computing, and the physics behind modern technology, subscribe and stick around.